Hello.
Okay, everyone. It's my pleasure to introduce Dr. Quinn Konopacky, who is joining us from the not so longer frigid realm of Toronto. I think it's defrosting now. Dr. Konopacky got her PhD at UCLA in 2009, working with advantageous on a subject close to my heart, brown dwarf binaries. She has since gone on to make seminal contributions in exoplanet research, which she's going to share with us today. So I'm not going to go into too much detail on that to not steal her thunder. But I should say that she has made some really phenomenal measurements with some of the best instrumentation on the planet. In my field, she made the first measurements of the actual orbital radial velocity orbits of brown dwarf binaries, which was absolutely fundamental in testing whether the evolutionary models work. This is a great result that I cite all the time. And she's also worked on the Galactic Center. She's an expert in adaptive optics research, and so she's used that to her advantage in all realms of science. And currently, she's a Dunlop Fellow at the University of Toronto. And today, she's going to be speaking about her work on orbits and atmospheres of directly imaged exoplanets.
Yes. Adam is one of my heroes. That was like the nicest intro ever. Okay, so thanks so much for having me. I've always wanted to come to UCSD. I've never been here before. So it's been great to visit and be in the sun a little bit. So today I want to talk to you, as Adam said, about some of the work I've been doing recently on trying to understand both the orbits and the atmospheres of directly imaged exoplanets. And as sort of a nice illustration behind my title is a very pretty artist's rendition that we got made a year ago that's supposed to show some of the planets that I'm going to be talking about while they were forming in the artist's head. So more on this soon. So here's a quick outline of what I'm going to talk about. So first, I'm just going to do a quick overview of some of the direct imaging discoveries that have happened so far and where we are right now with that. And then I'm going to talk in detail about the results from our ongoing monitoring campaign of one of these directly imaged multi-planet systems, which is called HR 8799. So we have both an imaging program specifically designed to try to do high precision astrometry, and also a spectroscopic program that I'll talk about as well. And then I'm going to talk about some results from an instrument that I've been working with very extensively, staying up all night working with. This is the Gemini Planet Imager. So I'm going to talk a little bit about some of the results from our calibration of the instrument and upcoming milestones for this instrument as well. And then finally, I'm just going to conclude with some of where I think the future directions of this field will go in the next 10 to 20 years. So I didn't want to go too far without highlighting the very, very large list of collaborators that I have. So for the Keck HR 8799 program, this is just a much smaller list than the number of people that work on the Gemini Planet Imager. As people know, instrument projects require huge numbers of people to make them successful. And so it's been really amazing to work with all these really talented people. The color coding is actually supposed to denote different things about them, but these two people in purple are two people also at the University of Toronto that I work with extensively, in addition to all the others here. Okay, so first I want to start with a little bit of a history lesson. So this was the state of what we knew about planets in 1988. So here on this axis, I'm plotting the mass in Jupiter masses as a function of the semi-major axis. So in 1988, obviously we knew of one solar system, and that was our own solar system. So here's where the solar system planets actually fall on this diagram. Some of the smaller ones actually fall at the bottom on this scale. So now, obviously, since then we've made some discoveries. So let's fast forward a little bit into the future. So here's planets known as of 2004. So this is right after the era, I think, of big boom in discovery, primarily with the Doppler method of detection. So each of these different colors represents the way in which these exoplanets were discovered. So you can see the majority on here in 2004 were known from the Doppler method. We were starting to get a few discoveries with transits, a little bit of microlensing discoveries, but you might notice that there's this giant gaping hole here in the top right portion of this diagram. So you could say I plotted it this way on purpose, but you could also say that we really didn't know anything about this parameter space in terms of if there were any planets out here, large planets at wide separations from their star. But now we know that these actually exist. So I think the beginning of the direct imaging era was in 2004, so that's why I picked that date. So the first directly imaged planetary mass object orbiting another star is usually credited as being 2-mass 1207b, which was discovered in 2004 with the VLT. And since then, there have been a number of really interesting objects that have been discovered. So, for instance, the planet, or not planet, depending on who you are, Fomalhaut B, was discovered with HST in 2008. And then this really awesome discovery of Beta Pic B in 2009 with the VLT. And then basically every large ground-based telescope has some sort of direct imaging program now. So there have been a lot of discoveries coming out here and there. So this is not by any means a complete gallery of all of the discoveries. But we also had 2 really interesting ones last year. Another one with the VLT right over here, this little 3 Jupiter mass guy, and one with Subaru. So we're starting to learn a lot more about this population. So my favorite, and the one I'm going to be talking about extensively, is HR 8799. I mentioned it in the beginning. And this is still currently the only directly imaged multi-planet system, so where we've seen directly imaged more than one planet orbiting a star. So HR 8799 itself is an A star. It's about 30 million years old. It was originally discovered in 2008 with both Keck and Gemini to have 3 planets orbiting it, so they discovered B, C, and D at that time, and then we went back and did a little bit job analyzing our data and pulled out E, which was interior to the other 3. These are our best estimates for the masses of these planets. I'll talk a little bit more about why we think these are the masses, or at least the upper limits on the masses, somewhere between 5 and 7 times the mass of Jupiter. So they're pretty heavy, and their projected separations are actually quite large. So the closest one that we see is about 15 AU separated from the star, all the way out to almost 70 AU for the outermost planet. So this is a large, wide population, or multi-planet system.
This is very young.
30 million years, yes, quite young.
And are there ways to find ones that are closer on that system?
I guess I'll talk about that at the very end. The better instrumentation should be able to push in a little bit further. So if we think with GPI, we can actually get a little bit closer.
Doing Doppler on it.
It's hard because it's an A star, and it's also young. So it doesn't have the lines, and it's also young. Young stars are hard for Doppler.
Apparently, I have to face on too.
Yeah, also face on.
Sorry, it is face on?
It's close. It's not exact. Yeah, I'll talk about that too. But it's not quite face on. But you can see that these arrows actually point the way that they're orbiting. So it looks, just from looking at it, it looks like it should be probably close to face on. But it's not exactly face on. I keep flipping back and forth. So now we're fast forwarding to 2 years ago now, 2012. So you can see that now our little orange points finally show up on our diagram. So we're finally having discoveries of these direct image things that live out in this region of parameter space. So you can see I had to make the dots really small for Kepler because there have just been so many discoveries with Kepler that it would just totally wipe out everything over here. And the other populations have been continuing to march on. Other discoveries have been made with Doppler as things push down to lower and lower masses. So you can see I switched the axis to actually Earth masses now to be able to show some of these Kepler objects. So as what I look at when I think about when I look at a diagram like this, and what I really want to understand is, as we have separated everything in terms of the way it was discovered, but does this actually represent sort of one continuous population, or are we looking at things that possibly formed in different ways? So what I want to understand is, do the things that live out here that we can actually directly observe, is this represent a continuum of formation, or do these things form in a different way from some of these Doppler planets? And how can we possibly find ways observationally to constrain the way that these planets form? So are there any ways that we can, at least with the current models of planet formation, even explain directly imaged planets in the first place? So planet formation is kind of often set up as this big battle between these 2 different competing models. It seems like most of astrophysics has 2 competing models that are fighting all the time. But that's kind of the way I see it, is the 2 most popular models are the gravitational instability model and the core accretion model. So first, in gravitational instability, what you have is basically a very large, massive disk, and then little areas of the disk basically become unstable and collapse, and then you get these little seeds of planets that then grow a little bit larger with more accretion, and eventually, hopefully, become stable and form a planet. And separately for core accretion, what you have instead is the gradual buildup of solids into larger and larger planetesimals, so that you get to a big enough, basically, planetary core. Something roughly about 10 times the mass of the Earth is big enough, and at that point, you could actually start accreting a very large gas atmosphere to make your Jovian exoplanet. So those are very basic explanations of these 2 models. So how have they actually done at comparing to observations? So starting with core accretion, this is the most popular model for explaining the close-in planets, so these Doppler planets, for instance. And it's been very successful at doing that. So this is a figure from a paper by Ida and Lin in 2004, where they modeled planets that could have formed via core accretion. And so this is the results of their simulation. So they had, in red, these are the gas giant planets. These are the ice giant, or the ice planets like Neptune, and then the terrestrial planets are in green. And so at that point, we only knew about gas giant planets, and these are observations, but you can see actually that the gas giants actually line up pretty well with their models. So this was a good sign for this formation mechanism. What's been difficult is trying to get this mechanism to work for the much more widely separated Jovian planets like we see in direct imaging. So this is an example of how this is difficult from a paper by Dodson Robinson in 2009. And what they were trying to do was look at different disks around different kinds of stars of various masses and see how far out they could get a large enough core to form such that they could then make a Jovian mass planet. And so what is plotted here is the mass of the core as a function of distance. And what you can see basically is you need to get above this critical line here to be able to have your planet form. And even for the most massive disk around the most massive star, the farthest out they can get the formation is about 40 AU or so. So not out where a lot of these planets have been discovered. So this
in
is
this model, how do the stars, how do the planets get ejected? You know, you have a local collapse, right?
in
How do they get ejected from the mass of the star?
I'm not sure I understand.
They don't start out as part of the bits.
They come from the nebula around it.
Oh, I'm sorry. Yeah.
I thought they were made locally. Okay.
No, yeah, no, they're made in the disk that happens to exist after.
This is not
Can't get into the star because it's a little.
Okay. So this is the situation that we have if we look at it this way. So we have this model, core accretion, has the ability to form two of the planets in this HR 8799 system, but not the outer two. So basically, you might think this is a problem, that you probably want all your planets in the system to maybe form in the same way. So this is an issue for explaining the system. So I'm talking about the gravitational instability method instead. So this has often been invoked as a better method for forming these wide planets and has often been favored. And so this is a snapshot of some simulations by Vorbov in 2013, where they again simulated a massive disk, and it would collapse at various times through different time snapshots. And you can see that lots of different little planetesimals form at different times, but eventually you get down to about 2 million years or so, and you have one that survives at large separation. So I know this is a little bit hard to read, but the axes say minus 1,000 to 1,000 AU. So this is a planet on a wide separation that managed to form in this method.
When they do those kinds of simulations, if they zoom in, they also get planets on smaller scale? Smaller separation?
No. Well, they do, but here's what I was going to say. They have trouble making them closer to than 40 AU, basically. So they can get them basically almost at the exact same location that the other method fails from the inside out. So that's been shown by multiple authors. That's sort of a cutoff. In addition, another issue with this particular method is that there's an expectation that if this was really efficient, you'd have this large population of very widely separated brown dwarfs that should be seen around stars. And as many people know, this population just doesn't exist. There have been a lot of surveys that are sensitive to this population. And finally, you also note from that snapshot that there were a lot of different little fragments that formed and didn't remain stable. So they have a very difficult time often making these fragments stay stable and go on to form planets. So now we have this situation. So for gravitational instability, ignoring all of those issues, but just looking at how close in they can get, we can form the outer two planets, but not the inner two. So what is going on here? We probably don't think that things, again, are forming in two different ways. So what we want to look at, and what I want to try to understand, is if there's a possible way to constrain observationally the formation mechanism of these planets. Are there any signatures or fingerprints that we could look for to maybe come back and say which model is working here? So there's a couple of things that I have decided to use. So one of them is orbital eccentricity and the dynamical properties of these multi-planet systems. So there's been some simulations that suggest that eccentricity, for instance, can be used as a tracer of formation. For instance, if something in a multi-planet system formed closer to the star, and then through dynamical interactions, some of them got scattered out to larger distances where we now observe them, there might be a signature of that in the fact that they would have high orbital eccentricity. So what this is a simulation from Chatterjee in 2008, where they started with 3 planets. And then one of them was ejected, but 2 of them survived in many of the simulations. And so the black dots are the innermost surviving planet, and the red ones are the outermost. And what you see, and this is the eccentricity as a function of separation, for the ones that are out here at the large distances that we're observing these planets, you have very high eccentricity. So it's possible that we could actually see these very high eccentricities if we do orbital monitoring of these planets.
So is that different than just the thing of planets moving in and out?
That's different than migration. This is scattering, yeah. Migration's a whole other complicated issue that I'm going to gloss over. So here's the other formation process fingerprint that we can use. So it's been suggested that there could actually be a chemical fingerprint in the atmospheres of these planets. And one of these models was put together by Karen Oberg in 2011. And what she looked at was where the different ice lines actually are in a protoplanetary disk. So where, for instance, the water will freeze out into solids, or the CO2 will freeze out. And so she saw each of these different colored bands represents the point at which the things have frozen out. So this is the ice line for water, and then CO2, and then CO is up here. And so, for instance, if you were looking at, say, your planet was at 20 AU around a G2 star, you'd be living in this region. And if your planet formed via core accretion, you might expect something like an interesting or different carbon to oxygen ratio than you would get if it formed via gravitational instability. So I'm going to talk about that a little bit more shortly, but what I wanted to just point out was that this is some possible fingerprint that we can use to try to understand how these formed. It's a possible way of testing formation scenarios. So that leads to the follow-up campaign. So first I want to talk about our astrometry and orbit part of our follow-up campaign. This has all been done with the Keck telescopes out in Hawaii, primarily the Keck 2 telescope, which is where the AO system is, as that is critical for our success. So let's come back to why did it take so long to actually be successful at directly imaging planets? Why was this basically the last method that was successful of planet detection? And direct imaging is often described as staring down straight into a spotlight and trying to see like a tiny firefly right next to it. It's just really, really difficult in terms of contrast. So the biggest problem is a contrast problem. So looking for the faint planets next to the stars that are very bright. So here, now to describe that a little bit more quantitatively, so now what I'm showing is basically a notional population of exoplanets. So each of the different colors here represents a different kind of planet. And this is the separation in arc seconds of those kinds of planets as a function of, or the contrast as a function of separation, basically. So you see that the terrestrial planets, the blue ones, are down here at really, really high contrast. So these are effectively extremely, extremely difficult to see. But for instance, if you look at something called the self-luminous Jovians, so these are the Jovians that are a little bit younger, so they're still radiating their own energy from formation, the contrast actually isn't so bad, but it's still somewhere 10 to the minus 6 to 10 to the minus 7. So it's a really difficult.
How is contrast? I mean, is it nemesis? What is the baseline for comparison?
The flux of the star versus the flux of the planet, basically.
So the total flux of the star in this wavelength band, and
yeah, at this location.
And just over what radius, or just over the radius of the star, or is it?
It's just a measured.
You're just saying all the light you can see from the star versus all
Yeah,
the
yeah.
Is it so it's volumetric in this wavelength band?
Yes.
Total.
Yes. This is, yeah, it's at 1.65 microns, so it's at H band, this particular one. So this makes it basically really, really hard because not only is the contrast huge, but look at the radii and arc seconds. So you're looking, these planets live somewhere between 0.1 and 1 arc second, so well below the seen limit.
That's the distance from the star?
Yeah, the separation. So we obviously have been successful. What do we need to do it? What are the things that we need? So the first thing you need is a large telescope. So typically, as I said in the very beginning, most of the programs use the ground-based telescopes, the 8 to 10 meter class telescopes. In addition, you really need diffraction-limited resolution because most of these planets are separated by less than about an arcsecond. So this leads to us to require adaptive optics. So just to make sure everyone is on the same page about adaptive optics, I wanted to do just one little brief primer on it. So adaptive optics is what we do to measure and correct for the atmospheric turbulence to go from a blurry scene limit image to a nice sharp diffraction limited image. So what we use is some sort of guide star. In our case, we're using a natural guide star so we can actually guide on the star itself. And we use the light from the star, we send it to the adaptive optics system. We measure basically the turbulence in the atmosphere, the deforming of the wavefront due to the atmospheric effects. Send that information back to a deformable mirror, which bends and moves like a funhouse mirror to perfectly correct for the distortion of the wavefront. And then you send that to your science camera. So that's very, very quickly how adaptive optics works. So it makes perfectly sharpened images for us to be able to look for planets or galaxies if you're interested in those too. So now coming back to here. So what are some other things that we need? So one thing that's really, really helpful and important is young target stars. So on that contrast diagram, what I showed was that the younger stars actually have better contrast. So actually target star identification is one of the most difficult parts of this game, basically, is trying to figure out what stars are actually young. It's quite difficult.
And that's just because the planets are brighter.
Yeah, the planets are brighter, so the contrast is better.
So it's not just reflected light.
That's right. No, it's its own light, basically, thermal. And then finally, you need advanced data processing techniques. So this is something that's been a really, really active area of research, is people trying to figure out better and better ways to pull the signal from the planet out from the data. And so they've come up with all these interesting processing techniques that have acronyms associated with them. So angular differential imaging, locally, you'll hear these things thrown around a lot in direct imaging. One of the major issues here is that all of these processing techniques actually introduces biases in both your astrometry and your photometry. So these are things that now we're looking at and trying to figure out how we can correct for these biases to actually get really precise astrometry and photometry.
What fraction of light is reflected? Negligible?
Negligible, yeah. Yeah, so all of our work is in the near infrared, and so even there it would be less. So.
And you can't just block the light from the star?
We do that too. So you also require a coronagraph too. So, which I will show you. Although it's difficult to see. There's actually, because of the way this image is stretched, there's a little chronographic spot that we use. We put the star behind it. And it's actually introduced some biases itself too, which I'm not going to go into in this talk, but there's been some difficulties just using the coronagraphs as well. So this is a little animation that's demonstrating how we take our data and shows you just what the data looks like. So this is basically the kind of information that we're working with when we take raw data. So what we're dominated by in terms of noise is the scattered starlight, which we also call speckles. So you can see that basically all these little blobs completely wipe out any planet signal if you just took an image, because they're all about the same brightness. So what we use in differential imaging, one of these acronyms, you basically turn off the counter rotation of your telescope. So you basically allow for the sky rotation to occur. You don't correct for it. And what that allows you to do is see real objects moving around as you go through your observation. So if you look very carefully right there, you can see a little planet moving by. And then what that gives you is a library of point spread functions that you can use to subtract from each image so that you recover the signal of the planet, like here. Now you can see them much better because the PSF is removed. And then if you stack them all
Those are planets?
Yeah, these are planets.
So what's orbital period? I mean, this is...
The orbital period for...
Those
Oh, this is
rotating.
the sky. Yeah, this is over
So
time.
how do you know it's a star, not a star?
Oh, well, that you have to figure that. That's another major problem. So most of your people will spend a lot of time discovering background objects, and so you have to come back like a year later and see if it's moved or not. Yeah. So in this case, they all move together, so we know they're not background objects. And then when you stack everything together, you can see the planets brightly show up, and you derotate everything. So this is just to demonstrate how difficult it is to pull out the signal and how much noise we're dealing with.
Is this a simulation or?
No, this is real. This is real data.
And what's the contrast on those planets?
It's about 10 to the minus 6.
So inside the square, you're saying you could never get in there.
Oh no, we can, and we have. So this is,
That one, right?
yeah, this is, yeah. You see when you stack it, you can actually, so something pops out from inside the square.
Is that the coronagraph?
No, the coronagraph is really small.
It's really.
It's just this part right here.
What is the square?
What's the size of this?
What's the size of this square? That's a good question. My guess is it's about an arc second, actually. And I actually don't know why they highlighted the square. Maybe just to show how when you stack things together, it looks better. I don't know why they highlighted the square in this movie. Okay. So once we account for all of our biases and get our data, we can actually do astrometry. So what we do is we've gone back basically twice a year, every year since these were discovered, to try to monitor these planets as they orbit. And our astrometric precision is about 5 milliarc seconds, which if you've heard a lot of the astrometry talks from some of the other groups that do astrometry at Keck, that's not super impressive. Usually they're pushing to below a milliarc second. But just the number of biases that we're dealing with, this is basically the floor that we're hitting, at Keck at least. But it's still good enough to start to do some orbital analysis and look for these eccentricity signatures, for instance, to try to come back to formation. So I've plotted the actual astrometry for each of the 4 planets, and so each of these colors I'll use again and again to represent the same planets. Everything is rotating this way, again, which is good, counterclockwise. And so we actually finally now have enough data that we've actually detected orbital acceleration, so curvature in some of the orbits of these planets. So we've measured curvature for these 2, and we'll measure curvature, we predict, this year for the other 2 planets. So we take this information and actually fit orbits, basically. So the way we chose to do this problem, or I chose to do this problem, was to basically look at every single planet, or all 4 planets, as basically just binary stars, and fit their orbits individually, and then hopefully recover information about the system in general from each planet independently. So for the most part, for our data, we used mostly just the Keck data, but there were some HST data points from 1998, which was before the discovery of these planets in 2008. So I think the people who took that data are probably really sad that they didn't discover the planets, but they went back and recovered it later. And so here's some of the different things that we're fitting for. So some of the properties, like I said, eccentricity, the inclination, period, semi-major-axis, etc., are the things that we're looking for. So some of the helpful things that have been done in the literature recently are that there was a pretty good estimate for the mass of the star, so we can fix that. And that was because they got a radius measurement with Chara that helped them constrain this mass. And there was a Hipparcos distance as well, so those things help us. And so over here, the astrometry is shown again, and now I'm just plotting example orbits over each of the planets. And so one of the first things that you probably notice is that our data actually is a really, really, really tiny fraction of the entire orbit, or our coverage is really small. And so although I've plotted example orbits, in general, an individual orbit fit is not really strictly interesting because you can imagine that a lot of different orbits probably pass through these points. So that's what I'm showing here now. So what we do is try to look at instead the distribution of allowed orbital parameters, or look basically for different orbital parameters that are ruled out by our data. So we do this through massive Monte Carlo simulations. And I think what you'll notice just from the plot of these allowed orbits is that while there are a lot that are allowed, there are different regions that things aren't allowed anymore. So we can actually start to make constraints on some of these properties that we're interested in measuring. So now I'm going to plot examples for the actual probability density functions for each of these different orbital parameters just for B. So I'm going to turn these wire diagram into histograms.
Those are fully independent at that point? The planets are independent?
Yeah, I'm treating them independently. Yeah. So here's histograms for each of these. I'm sorry, the writing is a little bit small. And I guess the point of this slide is that in spite of the limited orbital coverage, you can actually get constraints for some of these parameters. So there's 2 different histograms. There's one where we wait for the probability that we're actually observing the planet at the time the orbit thinks we're observing it. So that takes out, that allows for a lot of if we don't weight it, we get a lot of situations where the orbit fit favors something where periastron is right around now, which is not very likely. So if we take that into account, we actually get a better answer, I think. So
we should look at the dark
the dotted ones, I think,
Dotted
are,
ones.
yeah, the dotted ones are the ones, and I know this is hard to see, so I'm going to zoom in on the ones that I think are the most interesting. So that's eccentricity and inclination. So as you can see, in both cases, even when we don't weight, you can see that there's a pretty substantially strong upper limit on the allowed eccentricity for this planet. So you might remember from the diagram I showed in the beginning that we were, for that model that said that this thing could be scattered out, we're looking for eccentricities that are like 0.8 or 0.9. So that's ruled out basically with the data already. In addition, we can actually constrain the orbital inclination. So again, it's not perfectly face on. It's something probably somewhere between 20 and 40 degrees. And the nice thing is that all 4 planets basically give us the same answer. They all are favoring this inclination. So we can play other games in terms of now using information from one planet to constrain the orbits of the others. So if we force all of the planets to have the same orbital plane and assume there's no relative inclination between them, we actually get even tighter constraints on things like eccentricity. So now I've fixed the orbital plane of all the planets to be the same as HR 8799b, and I'm going to zoom in on eccentricity. And what you see now for all 4 of them is that basically, again, a hard upper limit of 0.4. So this is good that this is coming from the data, and it's as we get more and more data, the eccentricity upper limit seems to be coming down and down and down and down. And you might think, if you're a dynamicist, you're probably thinking this is maybe slightly obvious because these are large planets, and if their eccentricities are too high, you might get things that cause your system to go unstable. So it's actually good for the overall stability of the system that things are not too high. So the next thing that we do is take our astrometrically allowed orbits and feed them into basically a dynamical integrator to see what happens and see if those orbits are such that the planets will remain stable for the lifetime of the system. So what I'm showing you is what's happening for the majority of the cases that we run, which is that the system falls apart extremely quickly. So the innermost planet is already gone. You probably didn't even notice it leave because I was talking. But you can see now crossing orbits are bad, so that when you get these sort of interactions that happen between the others where things just go unstable really fast. So in general, you need the eccentricities to be low for the system to remain stable over the course of its lifetime. So this fell apart in about 5,000 years or so.
Isn't there also this intrinsic bias that you're more sensitive contrast-wise to hotter or younger planets? So is this strictly true for only those types where you have a certain contrast threshold, or is it generally true?
I think it's generally true for planets this massive, this close together. It doesn't matter that they're young.
So we just understand. So you're saying that to remain stable, they have to be on basically low eccentricity orbits
Yes.
because these are so massive and so far out.
Yeah.
But what about that theory that was saying that there should be high eccentricity massive planets this far out? Was that where there was just one planet?
That was where there was 2. So I haven't seen a simulation where they've done 4. So it's probably hard for the system. We wanted to test it anyway just to make sure. But once we started running the stability calculations, we saw that basically was just not going to work.
If you run the stability on your low eccentricity cases and your low mass ones, how long do they last?
Most of them fall apart in 5,000 years. So it turns out to be
not good enough.
It's not. It turns out to be really, really hard to make this particular system stable, which maybe means in the future it will be unstable. It's hard to know. At least it's been stable for about 30 million years.
So do you have any of your solutions that remain stable?
Yes.
Okay.
So very few. I mean, we like throw computers at this nonstop, and most of them fall apart, which is so frustrating. But the way you can get it to be stable is if the planets are in resonance. So we have my laser pointer's failing, but we haven't really found any solutions where the planets remain stable if their masses are as high as 10 Jupiter masses. So that's what sets sort of the upper limit on the masses that I was describing. So we can find solutions where some things between 5 and 7 Jupiter masses remain stable, which is what's expected at their 30 million year old age. So a few years ago, there was some controversy over the age of the star, but now I think that's mostly been resolved. And everything kind of hangs together, preferring these masses. So when we find it, it was noticed when the original discovery happened by Dan Fabricky and Ruth Murray Clay that the period ratios of these planets were actually really close to 1:4. And so they started experimenting with resonances to see if that would enhance the stability, and it turns out it did. So the solutions that we found that were stable were where these three planets, E, D, and C, are in a 1:4 resonance, and B doesn't participate in the resonance, actually, which is, I think, the same as the Galilean satellites of Jupiter. This is just to show, this is how you prove that things are in resonance, is if their angles are librating around 0. But interestingly, other authors have also been throwing computers at this question, and have found what they want is for all 4 planets to be in this very large 1:248 resonance chain. And so this is work by, my last name's Polish, but I can't pronounce these. And so they suggested that all of them have to be in resonance. And what that is really interesting for is to predict if any interior planets that we can't currently see with our systems now, where can we actually go and look for them if they're also in resonance? It gives it's pretty strong prediction of exactly where those planets should be.
Does the resonance have to do with the masses, or it doesn't matter? Does that determine the masses very well, or does it not? It's just a period system.
The resonance allows them to be this massive. So if they're less massive, they don't need a resonance. But the evolutionary models want these masses. They want them to be about 5 to 7 Jupiter masses. And for that to be the case, they have to be in resonance, basically. So according to these guys, they did several different calculations, and the exact places a hypothetical planet F would have to be if it's in another resonance chain. So that's interesting for future work, like with GPI. That's just it's a really cool system to be able to try to understand the dynamical properties of. But we think we've definitely ruled out any case where things could be very high eccentricity.
So is it okay to have some kind of hybrid picture then? So you just form planets in a disk,
Mm-hmm.
and the massive ones survive for a while if they're in resonance, and the other ones don't. They get kicked out.
That could happen, yeah. Or it could be that eventually the system will go unstable. It's only 30 million years old, so maybe it doesn't last for that much longer. And one thing that's been speculated is that these actually had to form closer in and then migrate out, and that's basically they got set up in the resonance as they migrated out in the disk. So that's
anyway, slice it. These things, these disks, these protoplanetary disks are planet factories. They're kicking out lots of planets.
Yeah, I think so.
This isn't a common system, is it? I mean,
It's not.
1 in a million or 1 in 1,000.
Well, we don't know 100. We don't know for sure. But there have been a lot of surveys that should have been sensitive to these exact kinds of systems,
So
and this is the only one.
It's okay to have a resonance setup.
Yeah.
It doesn't
Yeah.
seem contrived.
Yeah. Okay. So I'm going to finish the dynamics part now and move on to the second part of the follow-up campaign, which has been on the spectroscopy and the atmospheres. Again, with Keck. So just when these planets were first discovered, and this is something that's been coming up again and again in the literature, is that most of them are discovered with imaging, so the only spectroscopic analysis tools we have are photometry. And so what we like to do is put them on HR diagrams, or color magnitude diagrams, basically. So what I'm showing now is a plot from this paper that has a J minus H and an H minus K color magnitude diagram. And it's plotted a bunch of the different directly imaged planets that have been discovered, along with the canonical field brown dwarf population. So the L dwarfs live here, the LT transition down to the T dwarfs. And what you'll notice is, at least for the HRA 799 planets that I'm interested in, they kind of live in a region of parameter space that there isn't really much else. And they definitely don't match what they were expected to, which was the field T dwarf population, because they have similar temperatures and similar masses, basically. So it was expected that they should be bluish, but they were seen to be quite red. And so that allowed people to speculate about what was going on in their atmospheres, but it didn't give them a very good handle, I don't think, on what was actually going on or say anything about the atmospheric chemistry. So that's why spectroscopy is so important. So the best tool to use for this, I think, is integral field spectroscopy. And there's this amazing integral field spectrograph at Keck called OSIRIS with the AO system. And we can use it to characterize things much better than we can with photometry. So far we've targeted 2 of the planets in the system, the outermost 2 planets. So these white boxes represent roughly the field of view of OSIRIS. And so this was the field of view and the orientation we actually used of OSIRIS with respect to this star when we targeted these. And we did that on purpose for this reason. So again, the main source of noise that we have and the main difficulty that we have is the speckles or the scattered starlight. And so the nice thing about the IFS, so what I'm showing here now is a movie that shows a rectified IFS cube, and we're stepping through in wavelength. So for each image is at a different wavelength. And what you'll notice is that there's stuff moving across the field of view, and those are the speckles. So the speckles position actually is a function of wavelength. So we use that fact, and the fact that the planet's position is not, so if you look closely right here, there's a little dot that isn't moving with wavelength. And that's a planet. So we use that to subtract them out, and I think recover nicely the signal from the planet, separate from the starlight. So what have we learned? So this is data for HR8799b, the outermost.
You only get about 3 or 4 different wavelength bands or something like that? Is that...
No, there's like 1,600, so it's not showing every single slice. It's binned. So the first work that we published was in 2011. This was led by Travis Barman for HR8799b. We had good data, but not a lot of data. So OSIRIS's nominal resolution is 4,000, but we had to bin our data to get good signal and noise for this particular planet. And this was a good work, I think. So there was a couple of interesting things that we noticed. So here's the spectra. So we had an H-band spectrum here and a K-band spectrum here. The data points are actually photometry to show that the spectrum is roughly consistent with most of the photometry that had been taken. A couple of things that we noted in this paper were first that people who look at brown dwarf spectra and try to prove that they're young look for this triangular H-band. So again, there was some controversy over the age of the system for a while, and so that was one of the first things we pointed out was that our H-band looks somewhat triangular. We also, because the colors were so red, people invoked dust to explain them, and that was also necessary to explain the spectroscopy as well. So there's definitely thick photospheric dust in these planets, for sure. And then we also noticed that there was only weak methane absorption in the K-band, where we were expecting it to be much stronger. So that was suggestive of non-equilibrium chemistry occurring in the atmosphere as well. So now, moving on to the other planet, so HR8799c. So this planet is a factor of 2.5 times brighter. It's a bigger planet than B, but it's also twice as close to the star. So these two collapsed OSIRIS data cubes are on the same stretch. So I think if you squint, you can actually see HR8799b pretty easily amongst the starlight or the scattered starlight. But C, I think, is completely wiped out. So it took a lot of effort to basically try to make sure we knew exactly where the planet was and then extract its spectrum. But we think we managed, and so we basically used the same technique where we looked at the change in wavelength of the speckles to subtract them. And then this is, when we actually do that, we recover the planet, I think, pretty well. And then in this case, the star is over here. So the first thing that we wanted to do was compare our new spectrum to the other spectra for exoplanets that had been taken so far, at least for directly imaged exoplanets. So to do that, we binned everything to the same resolution and plotted them on the same plot. So this is the flux as a function of wavelength. For this particular planet, we only did the K-band, around 2.2 microns. So now what I'm showing is our planet spectrum here. It's shown in black. This is HR8799b, which I showed before. And this red one is the spectrum from another planetary mass object that had been taken with Symphony at the VLT. So this is 2mass1207b. And one of the best things about this plot, I think, is that all 3 of them actually look different. So sometimes we like to say that we're starting to be able to put together a spectral sequence for exoplanets to be able to compare to future observations, hopefully. But the nice thing about this particular data set was that we had 5.5 hours worth of data just on this one planet alone. And that gave us sufficient signal noise that we could actually extract the spectrum at the full resolution of OSIRIS, so RF4000. So now I'm showing the spectrum in black again, but at the full resolution. The green actually is a best fit model, atmospheric model. So our best fit temperature is about 1100 Kelvin. and I think it matches relatively well. What's also highlighted are regions where different molecular features should be important in the K-band, so things like water and CO and CH4 are important. And another important thing to note is that while some of it looks kind of noisy, the majority of these features actually match things that are in the model. So the majority of these are actually real lines rather than noise. And most of them are water. So
how do I read these brackets? Are they pointing to a water line?
It's just this whole area is,
whole area.
yeah, this whole area is water.
These are rotational bands for water?
I think so, yeah. And methane and CO.
And is that dip at 2.3, is that by carbon monoxide?
Yes. This is something that people who stare at a lot of spectra would say obviously, but we ended up having, we wanted to prove it, so I'm going to talk about that in just a second. What this really does, I think, is highlight the power, and this has been basically the promise of direct imaging, is that you can, because you can separate the light of the planet from the light of the star, you can throw a spectrograph on it. And that just gives you so much more information than you can get via, for instance, transit spectroscopy, which has been the main way that people have studied planetary atmospheres so far. So just for comparison, this is what the spectrum would look like if it had typical transit spectroscopy resolution at K-band. So you just basically get nowhere near the richness of information that you get for the directly imaged exoplanets. So now, again, coming back now to the species that we are seeing in the spectrum. So we decided to make sure that we could prove what was actually there. So what we did was generate synthetic atmosphere models composed entirely of one molecule. So we made one of methane, water, and CO. And those are the different colors here. And then our spectrum is shown in red, and we've removed the continuum to just focus on the lines. And then we cross-correlated each of these with our spectrum. And that's what's shown down here. So here's the correlation for each of the different models. So you see that there's a pretty good peak for water and CO, but basically no peak, again, for methane. So even if there was really weak methane, so this is something that we were looking for, this method of detection would be much more sensitive to it, and we still are just basically not seeing any of it. So if it's there, it's very, very weak. And then the black one is if we put basically all of this together into a full atmosphere model and we get the highest peak for that, so that's comforting, basically. Our atmosphere models are pretty good.
Do the theoretical models expect you to have methane at the same time as water and carbon monoxide?
Usually water, yes, but not carbon monoxide.
Water and methane in significant amounts?
Yes. So now I'm coming back to trying to constrain formation. So as I mentioned in the beginning, there are these models that said based on where different species froze out in the disk, you might actually see a different abundance of carbon to oxygen than you would expect if you didn't have these things freezing out and formation via core accretion. So what we did was we took these sets of models, so they gave us a set of abundances in these models that we could expect at the location of HR8799c, and made a bunch of different synthetic spectra. And so basically here's some comparisons between the data and the models, and this is all just to point out that this was the best fit. So C over O equals 0.65 is our best fit. And so what we've ruled out is things that are very high C to O ratio, so about 0.9, and very low are also ruled out. So for instance, there's a big feature here that's not matched in our data. We have a little bit of uncertainty on this, so we did a Monte Carlo simulation to determine what our uncertainty on this ratio actually was. And so you might think, well, what's 0.65? What does that number even mean? So basically, in isolation, it doesn't really mean anything. What you have to do is compare it to the C to O ratio of the host star. So the stellar value for HR8799a has been measured to be about solar. So the solar value is 0.55. So that means that this planet is very slightly superstellar in C to O ratio. And now what does that mean? So does this mean that this is evidence that this planet actually formed via core accretion? So what I'm now showing here with my broken laser, okay, it's broken.
Can you use the other?
The top one. Okay, perfect. This is way better. So this is now just a cartoon of HR8799 and what its disk might have looked like shortly after it formed. So, and it highlights important locations in the disk. So the H2O frost line is right around 10 AU, and then the CO2 frost line is right around 90. And this region right here is the location where the HR8799 planets are seen now. So they live in this region where water is now largely in the form of ice grains, and so therefore a lot of oxygen is depleted from the gas phase. So that gives you your elevated C to O ratio. So a very simple model would suggest that if you had the same value as the star, so this 0.55 value, that would imply, or that would be what we would get if it formed via gravitational instability, because everything in the disk would just collapse all together and it would all be mixed. So you wouldn't see this distinction. But you would get superstellar if you form via core accretion, because your solids are going into your core, and then your atmosphere consists of what's left in the gas, which has this larger C to O ratio. So we have neither of these. We don't have 0.9 and we don't have 0.55. So what does this mean? Well, to get anything superstellar, it still suggests formation via core accretion, but you might have to have a little bit of subsequent solid accretion in the atmosphere, so planetesimals bombarding the atmosphere.
What's the uncertainty on the CDO ratio of the A component?
That's a good question. It was measured in like 2006, and it should probably be redone.
I mean, it's pretty close.
It's close.
To your errors, it's within 2 sigma. So
yeah, it should be redone. Yeah.
You had said migration was another question.
Yeah.
How would that affect these ratios?
So I think this might be naive, but I think it would be difficult to have all 4 of those planets packed in here when they initially formed. So at least some of them probably should have been beyond 10 AU. So if they all formed close in, I think at least some of them should have been here before they migrated out. So this region is quite wide, between 10 and 90 AU. So one of the things we want to do is measure this also for the other planets and see if it's the same. But again, migration makes things really complicated because you can get them forming at a lot of different distances. So that's the very tentative picture that maybe we can say something about the way these planets formed using this kind of analysis. So one last thing I'd like to say about this particular system is that it really is one of the most analogous systems that we've even seen ever to our own solar system. So they're much larger than the planets in our solar system, and they're much more widely spaced. But if you basically scale it, what you can see is that you have basically 4 gas giant planets or giant planets at large distances, and then you also have these 2 belts of material that were found with Spitzer. So you have one that's interior to the innermost planet, kind of like the asteroid belt, and you have something out here, kind of like the Kuiper belt. So if we think that this formed via core accretion, and that's the favored model for the formation of our own solar system, it wouldn't be surprising for there to be more possibly terrestrial planets lurking interior here. So this is an amazing system to study, I think, in the context of our own solar system. Okay, so that's all for that system, and now I want to move on to the future. So this is projecting, again, we're coming back to our plot. So here again is mass as a function of some major axis. And this is what I hope this diagram will look like in about 2016 or so. So Kepler, again, has been taken off because it would flood this entire area. But what should be focused on is now all these nice orange dots out here at large separations. So I'm hoping in the next couple of years that there will be a lot more discoveries with direct imaging. And that's because there's a lot of new amazing instrumentation that's just now coming online that should fill in this region. And the instrument that I work on, as I mentioned at the beginning, is the Gemini Planet Imager. So, which we call GPI. GPI was a roughly $20 million project built by a consortium of institutions in the US and Canada. It was PI'd by Bruce McIntosh, who was at Lawrence Livermore and now is at Stanford. And parts were built at UCLA, HIA, University of Montreal, American Museum of Natural History, and it was all assembled at UC Santa Cruz. So the Gemini Planet Imager is on the Gemini telescope, the 8-meter Gemini telescope. It's on Gemini South in Chile. And this is a picture of it hanging off the back of the telescope. So that's GPI right there. And here's happy GPI team members helping install it on the telescope. So we actually finally just achieved first light on November 11th of this past year, which was a really exciting milestone. So since I work at a place that does a lot of instrumentation, I wanted to show the Lego man in comparison to GPI. So GPI is about the size of said Lego man, or a person. It has 3 major subsystems that were built in part or in full at these different institutions. So it has a really advanced adaptive optics system to get rid of some of this speckle noise that you could see in our Keck observations. And then it has a calibration unit that helps take out anything that's left over that the advanced AO system doesn't correct. And then the science detector is actually an integral field spectrograph. So for every single object that's discovered will get a spectrum automatically, because it's just so important to be able to characterize these things spectrally to understand their atmospheres. So things have been going super well, as you can see. Here, commissioning runs have been highly successful. There was uncoordinated jumping occurred right after the first light run, so everybody was really excited. Things went really well. Shortly after taking its first images of stars and things like that, GPI got its first image of a planet. So this was one of the planets I showed in the gallery in the beginning, Beta Pic B, around the star Beta Pic. So this is a 1/62nd image with GPI. So this is a rectified data cube, again, because it's an integral field spectrograph. So the planet is right here, and it's a collapsed cube. So there are still some speckles and things, but the most important thing about this particular image is that in 60 seconds, we got the signal noise on a planet that current systems take an hour to get. So it's basically the most powerful planet imager in the world right now.
So the way this thing works, it takes out the disk plane, or is that small compared to this?
You mean the Beta Pic disk?
Yeah.
It's not detectable in this mode. Yeah.
What's the contrast here in this case?
It's about the same, 10⁻⁶. But you can see how much better the speckles are suppressed with GPI. So it just stands out much more brightly in comparison. So when you actually stack everything together with a half an hour worth of data, you see this planet stands out much brighter. So this is a beautiful image that was recently published in a paper in the Proceedings of the National Academy that was led by Bruce McIntosh, describing our first light. And there's a paper in preparation by Jeff Chilcote, a grad student who's graduating this year at UCLA and is actually coming to the University of Toronto as a Dellnut Fellow in the fall. And here's his spectrum. So this is the first planet spectrum that GPI has gotten of Beta Pic. This is an H-band. Again, it's young, so it's looking pointy, triangular. And the analysis is ongoing to understand what we can say about the atmosphere of this planet as well. So this is hot off the presses, unpublished work.
What's with the error bars?
What do you mean?
And they
They exist.
perfectly. There's not 1/3 of them more than one standard deviation away.
Oh, because, well, those are, like, this is just a line drawn through the data points.
It's not a model. That's just.
Yeah, that's the actual data. Yeah, yeah. Sorry.
Connected dots get it.
Yeah. So hopefully your error bars, yeah. It's not a model. There's no model on this plot. So GPI, some people don't realize that GPI is also a polarimeter, and some of the polarimetry stuff has been the coolest stuff that I've been seeing coming out of this early commissioning work. So this is a well-known debris disk, HR4796, and here's the total intensity image and the polarimetry mode of GPI, and then here's the polarized intensity image. And you can just see how beautiful and amazing I think this detection actually is. So this is work being led by Marshall Perrin at Space Telescope. It should be coming out really soon. The debris disk stuff has been really, really cool.
Is the line then behind or in front?
I think it's in front. Yeah. I think. And also, GPI is like, I want people to realize that it's a multi-purpose instrument, so people use it for things other than planets as well. It does solar system objects, so that's a part. Some people on our team are solar system astronomers. So here's GPI's image of Europa, and this is a comparison to what was obtained with Galileo. I actually think it's a pretty nice image of Europa as well, and there have been a couple other solar system objects that we've done. So that's just the greatest hits of GPI as of right now. So what are the upcoming milestones? What are we working on right now? So there's additional engineering runs. So we just had one, actually. It happened last week. And then there will be one more in September. There was a really successful early science run, so that happened in April, and I think that they got basically all the programs that they selected for early science. GPI was open for shared risk observing. There was a call, so people can hopefully start using it this fall for actual observations. Right now we're working really hard on our on-sky calibration, so we've been spending a lot of time trying to constrain any issues that we have with both astrometry and photometry, because it's really important for what's coming up, hopefully this November, which is the start of the survey. So we named this survey the GPI Exoplanet Survey, GPIES. So this is going to hopefully start in November, and it's a 3-year campaign. It was a 900-hour time that was given to us by Gemini to do this survey. So what we're going to do is survey 600 stars looking for directly imaged exoplanets. So this is, the star list is basically already been selected. And hopefully, here's what we'll get is statistics. So it's primarily a statistical mission. But what we're hoping is these things will also come out of it that are really important for some of this other stuff that I was telling you about constraining planet formation. Like, for instance, high signal noise, near-infrared planetary spectra, the eccentricity distribution of these widely separated planets, and also some of this more cool polarimetry of debris disks. So in particular, the parts that I'm in charge of are doing the astrometric calibration. This has been a really interesting and fun topic to work on. And then working on also trying to understand if we can actually pull out the eccentricity distribution over the course of a 3-year campaign. And I think we actually can. So those are active areas of work. So that's GPI. So that's taking us through about 2017. So what comes after GPI? What's next on the horizon? So planning has already started for the next generation of high contrast images. We're always planning for 10 or 20 years in the future. So a lot of this planning is being done for space-based missions. So for instance, the W first mission is actually, they've decided they're going to have a coronagraph in it so that they can do exoplanet imaging. They're hoping to actually look at basically reflected light from things like super Earths. And so here's a simulated image of what they might see. Even further in the future, people are still talking about different kinds of TPF or terrestrial planet finder missions. So some of the more interesting proposals have been fly a starshade in concert with maybe a pre-existing telescope or a telescope that you put up there. But this starshade is 80,000 miles away from this and has to be flown to within basically like a meter or something of a position to be able to get images like this. So if we could build something like this, you could actually maybe start to directly image terrestrial exoplanets. So that's space. But what I'm really more excited about is what we can do from the ground. And I think that the 30-meter telescope is going to be an amazing direct imager for exoplanets. So it already has 2 instruments in the conceptual phase, designed specifically for direct detection. So again, now what I'm showing here again is this plot of contrast as a function of separation, and again a brighter now notional exoplanet population. So you have your gas giants, your exoplanets, your water ice planets. And so here's sort of the parameter space that will be carved out by the W first coronagraph mission. And then here's the parameter space carved out hopefully by these 2 proposed TMT instruments. So this one right here, this red line, represents an instrument called the Planet Formation Imager that's being proposed for the TMT. So hopefully it's going to be able to reach some of these super Earth planets that we know are very abundant because of Kepler. And then the other one that's being planned, and this is led by a Japanese team, is the second Earth imager for TMT. And it's going to try to do something crazy and probe even at closer separations to hit even a larger swath of this water ice planet population. So stay tuned, I hope. These instruments are a long way in the future, but I think this is where things will be very, very interesting in the next 20 to 30 years for direct imaging. Okay, so now I just want to summarize. So we've been able to vastly improve and spend a lot of time on our data reduction to be able to now look at the orbits of the HRD 799 planets. We've got accelerations. We've found scattering's unlikely. We've constrained the eccentricity and the inclination. The spectroscopy work that we've been doing is basically among the highest resolution that's ever obtained for any exoplanet, which we can use to constrain the chemistry of the atmosphere. GPI is ramping up. I'm super excited about it, and I hope to have a lot more to say about it as it continues to get close to actually starting the campaign, which is happening this fall. And I'm really excited about what TMT is going to do for direct imaging further down the line. So thank you so much for listening.
Thank you, Quinn. Any questions?
If their system has like littler planets inside, will any of those other instruments still find them, or are they still, how close can you get in? I mean, if you
Yeah.
And would those resonances continue?
I don't know. They could. They might not. I mean, there's probably, depending on the mass and the location of any interior planets. You might have them in resonance, you might not. It might be required, it might not for them to
When will we
remain.
know whether there's like,
And GPI should be able to see anything Jovian interior, so like the hypothetical planet F. GPI should be able to see that. And these two can definitely get closer in than we can get with GPI as well. So if there's any super Earth interior, we might be able to see it with TMT.
How many planets is GPI expected to see, and what's used in that simulation?
We hope 50.
Is that the same simulation that Bruce was showing 10 years ago, or has it been updated?
It's been updated.
Yeah.
So there's been multiple different iterations of that simulation. So it's been updated to account for updates in the known planet population with Doppler mostly. So it mostly comes, I think, from assumptions based on extrapolating from Doppler, which may or may not be the best assumptions, but 50 is probably optimistic. So somewhere between 25 and 50 is probably, hopefully, realistic.
And can it be moved to Northern Hemisphere?
It's supposed to be. So that was originally the plan, was that after X number of years, 5 to 10 years, it was going to come north. Gemini has funding issues, and they can only support 3 instruments at a time at any given telescope. And then they're going to make decisions about which instruments to support based on how popular they are, which is why I'm trying to sell like GPIES. Something can be used for other stuff, so people apply for it to do other things as well. So maybe, I hope so.
So interested in what you had to say about these things that get kicked out. I mean, a number of these big, massive ones, of course, are you can see them in their own light, right? I forget. You keep telling me what the lithium burning threshold is, but of order
0.06 solar masses.
Okay, so order a few percent of the solar mass, something like that. So you're getting roughly into that range, not quite that range, but even so, what's the prospect for detecting
This
these?
is 10 times smaller.
I understand.
Yeah.
That's close. Nevertheless, even without lithium burning, though, they're still hot. They're young things. They have a lot of radioactivity in them, and they've got a lot of gravitational binding energy they're releasing. So, you can actually see this light. So what are the prospects for detecting kind of rogue planets floating out there and doing spectroscopy on those?
I think they're good. I mean, I think we're getting to the point where we've now seen free-floating close to planetary mass objects, for sure. And I think that there will be more in the future. It'll just be interesting. I think what's interesting is to try to figure out whether they're maybe just a low-mass brown dwarf or a planet. So how do you tell the difference? And does that difference actually mean anything? Is there a point to distinguishing between them? I think possibly you could look at the spectra, so look for some of these spectral signatures. If we start to see that, for instance, all planets have these elevated C-O ratios, maybe if we looked at a field object and it had the same thing, we could tell, versus a brown dwarf, which wouldn't necessarily have it. But I think we're very shortly, if we're not already, going to detect free-floating planetary mass objects. And they see them in, they think they see them in star-forming regions too, where they're a lot brighter. So the prospects are good.
What were the temperatures of those models that were fitting in?
Around 1,000 Kelvin.
They're all about.
12,000 Kelvin.
Any other questions? Okay, thanks. Let's thank